Plutonium-239, the fissionable isotope produced by neutron absorption in fertile uranium-238. The process builds inventories of plutonium in the thermal converter reactors of a growing nuclear power industry. In fast reactor operation, more can be formed than fissionable isotopes consumed. Its nuclear characteristics make it valuable to thermal reactors and a superior fuel for fast reactors. Advantages to be gained by recovery, refabrication, and the use of plutonium in reactor systems include lower costs and a more efficient use of energy resources. To realize these advantages is a diversified and complex task. Due to high toxicity, fire, and criticality hazards, various regulations and methods for remote handling in alpha-sealed facilities have always been employed. In this facility, a variety of experimental plutonium fuels have been produced. For the experimental breeder reactor 1, a core loading of plutonium alloyed with 1 1/4 weight % aluminum was injection cast. Rough cut slugs were coined and densified, then assembled in zirconium tubes with uranium blanket pieces. Sodium-potassium alloy served as the thermal bond between the fuel and the cladding. Due to the small delayed neutron fraction for plutonium, the core's kinetic behavior was particularly sensitive to mechanical movement. The breeding gain was measured, and for every 100 fissionable atoms destroyed, 127 were formed. The close-coupled fuel facility for the experimental breeder reactor 2 is geared to handle highly radioactive recycled plutonium alloys. All facets of the system demanded extensive attention to design detail for remote operation, repair, and modification of equipment. The cycle involves disassembly, reprocessing, fabrication, and reassembly. Irradiated fuel is purified by melt refining. Volatile fission products distilled from the melt are condensed in the fume trap. Noble gases are vented. The purified melt removed is an alloy of uranium, plutonium, and controlled metal fission products. Elements separated through selective oxidation remain in the crucible. Work on advanced molten plutonium fuel concepts for fast reactors continues. Various combinations and concentrations of plutonium iron, plutonium cerium, and plutonium cobalt are readily prepared and held in high purity tantalum cans. These fuels are used in the Los Alamos molten plutonium reactor with sodium coolant temperatures in excess of 600 degrees centigrade. Analysis of fuel container compatibility and methods of fission gas removal while the reactor is running are of primary importance for the extension of the molten fuel concept to a large central station plant. The Plutonium Recycle test reactor has been operated since 1961 in an extensive program of fuel cycle development at Hanford Laboratories. Evaluation of many different types of plutonium-bearing fuel materials, claddings, and fuel geometries have been completed, and the core gradually changed to a uniform loading of 1 weight % plutonium-uranium ceramic fuel particles in zircaloy tubes. The reactor physics, chemical reprocessing, and fuel element technology associated with the mixed oxides of plutonium and uranium indicate reasonable fabrication costs and encouraging performance data for power reactor operation. To obtain uniformly enriched high-density fuel particles, plutonium oxide is first carefully mixed in with the uranium oxide. After thorough blending, the mixture is prepared for high-energy impaction. Seven kilograms of the fuel material fill each container. And for safe handling outside of the hood environment, each one is carefully cleaned and sealed in a second can. The mixture is heated to 1200 degrees centigrade. At this temperature, under the 400,000 pound per square inch impact loading developed, a solid body is formed from the powders. Plutonia is fixed in intimate contact with the urania, thus maintaining a uniform distribution. The impacted fuel material is 98% of theoretical density or greater, an important factor in producing high bulk density particle-containing fuel rods. High particle density is also needed for thermal conductivity and fission gas retention. A variety of these ceramic fuels are prepared in large quantities, and the different steps in production are segregated to allow for flexibility. Approximately 1,500 fuel rods with a 1.5 weight % plutonium uranium oxide were prepared for the experimental boiling water reactor. They are centrally loaded in the reactor, and with 36 rods to an element, fill about 1/4 of its new core. The reactor experiments are aimed at developing a calculation model for this fuel in a light water thermal system. Particle sizes for fuel tube loading range from about 5 millimeters in diameter to powder. From these, a mixture of the coarse particles and a blend of fine powder is prepared. The different size fractions help in packing the tube uniformly. Vibratory compaction was developed to load fuel tubes to the desired 85 to 90% of theoretical density. High bulk density minimizes the relocation of fuel during irradiation, provides for better heat transfer, ensures adequate reactivity, and furnishes support for the thin-walled cladding under high coolant pressures. A line of hoods is served by one electromagnetic vibratory unit. In each hood, a fuel tube is clamped to the bar extending from the drive unit. Then set up with a pre-measured quantity of fuel, funneled to the top of the tube. The high-intensity vibrations subjects the particles to a gravitational force of some 50 to 70 Gs. An optimum range from 300 to 1,200 cycles per second avoids grinding, and the frequencies are repeatedly scanned until the desired bulk density is achieved. Sealed and checked for compliance with specifications, the fuel rod is complete. An assembly of 19 forms the fuel element. plutonium recycle test reactor utilized in the evaluation of these fuels for thermal reactor application is a vertical pressure tube reactor moderated and cooled by heavy water. The tubes passing through the moderator tank contain shim rods and flux monitors, in addition to 85 fuel elements. 2 of the fuel locations contain experimental loops. One, an element rupture facility. The other, to study high-temperature gas reactions, such as carbon dioxide with graphite. Fine reactivity control is accomplished by regulating moderator level. As the helium gas pressure between the dump tank and moderator surface is changed, the liquid head moves to balance the pressure. Over a 10 to 12 day operating cycle at 70 megawatts thermal, the shim rods are periodically withdrawn to overcome long-term reactivity poison, and moderator level control is maintained between 101 and 109 inches. Shim rods are effective in adjusting the neutron flux pattern and controlling individual tube power. In the operation of plutonium-bearing fuels, several reactions take place. When a neutron is captured in plutonium-239, it yields plutonium-240, a fertile material. Subsequent capture yields 241, an excellent fuel. If a neutron is captured in 241, it yields plutonium-242. Experiments are underway to determine the rate of these reactions and their accumulative effect on reactivity. Test elements have been operated to failure to determine ultimate limits. And for the assurance of safety under undesirable conditions, deliberately defective elements are irradiated. Ceramic fuels have performed very well at power generation rates more than 4 times those utilized in contemporary water-cooled power reactors. Allied investigations ascertain void migration, fuel relocation, and the extent of the molten zone in the fuel rod. Unique laboratory tools are used in growing high-purity crystals with ideal density, and to measure electrical resistivity. A determination of thermal conductivity is obtained by subjecting one face of a sample to a laser pulse and recording the temperature rise on the opposite face. In the successive recycle of the mixed oxides of plutonium and uranium, the restoration of fuel reactivity is accomplished by reprocessing using a molten chloride solvent. Irradiated fuel is declatted by hammer action, then oxidized with air at 450 degrees centigrade to form U3O8 PuO2. Charged to a molten salt solution composed of lithium and potassium chlorides, the mixture is sparged with gaseous hydrogen chloride and chlorine at 600 degrees centigrade. Plutonium enrichment can be varied between 1 and 25% by adjusting the sparge rate and current density. The fuel material is recovered from the melt by electrolysis. The desired plutonium-uranium oxide combination, free of fission products, is plated out on the cathode. Then the high-density fuel is crushed to yield particles for reloading by vibratory compaction. Although detailed forecasts of plutonium utilization in a thermal neutron spectrum are not defined as yet, economic studies predict a sizable positive value for plutonium, and the wide spectrum of fueling possibilities attests to its versatility for nuclear power applications.